The Infinity FA tool is our standard etch platform, but it's been optimized for delayering applications. So it has a broad beam ion source for etching, it has a PBN for neutralization, it has a stage with tilt rotation and water cooling, and it has a load lock for quick sample turnaround, and it has the SIMS for endpointing. So the SIMS is critical to this application because, for instance, you can monitor the copper or tantalum signal as you etch through the chip, which allows you to automatically or manually stop the etch at exactly the layer you want, whether M6, M4, or the device layer. So delayering will always be an art that requires a variety of techniques for different applications. For instance, the FIB has the ability to drill down to a specific point of failure that's been pre-identified and even repair that point of failure by depositing metal. However, what the FIB can't do is image an entire chip and its structure. So this broad ion beam etch is complementary in some sense to other techniques. You can take a fully packaged chip or a chip that's only partially through the back end of line processing and bring it down to image it either for yield improvement, failure analysis, or even for reverse engineering, or investigating the product for security reasons. SIMS stands for secondary ion mass spectroscopy. So the way that works is when the ion beam hits a substrate, it ejects atoms, that's how it etches, and some small fraction of those atoms are ionized. Those are picked up by the SIMS. They go through a series of electric filters and then the quadrupole filter, which selects them by charge to mass ratio. So for instance, you have copper or tantalum with different masses, and you can monitor those signals over time as they come from the chip. So as you go through one layer, the copper signal will be high, and then it dips as you go through the via layer, and then it comes back again through the next trace layer. And as you get to those vias with their barrier layers, you will see spikes in tantalum or whatever other elements are there. And so this is key to the delayering application because instead of etching blindly, meaning you have to frequently vent and inspect the chip to see if you've etched far enough, you can know that you've reached the exact metal layer that you want. And in practice, when you set up a recipe, it looks like you are looking for usually either the rising or falling edge of the signal, and then you can include an offset. For instance, looking for the rising edge in the copper signal, and then wait 10 seconds to make sure you're fully in the metal layer before you take the chip out in order to image the entire design. The SIMS is excellent because the sensitivity spans 7 orders of magnitude. That means you can simultaneously measure the signal of the very thick copper layers of the interconnects, and also you can see very low signals such as the thin barrier layers. So the signal is not as strong as a dedicated SIMS metrology tool because the geometry is not quite optimized. The SIMS head has to get out of the way of the broad ion beam and also to protect the internals of the SIMS from the etch products. But the sensitivity is still there in order to be able to visualize these, the signal from these barrier layers. We have both available on the system, but we don't usually use them. So when you talk about chemical etching, especially wet processing, the etch rates between different materials can vary over several orders of magnitude. But in ion beam etching, it's primarily a physical process, and the etch rates between soft materials and extremely hard or refractory materials only varies by a factor of 2 or 3. And the other advantage is as you etch a single material, as you change the incidence angle between the source and the substrate, the etch rate will first go up and then decrease, and that happens over the range between 0 and 70 degrees. And that shape of that exact curve is different for different materials. So in practice, that means for 2 different materials, you can reduce the selectivity to near 1-to-1 simply by adjusting the tilt. Where you would introduce chemical etching is where that is not sufficient for your application. So you can introduce gases through the source or into the chamber, so both Ribby and CABE are supported. And generally we use those, for instance, a simple cleanup step to improve the planarity of the etch, or if you want to have a very high etch rate to get through very thick layers. So with our interface, it's relatively easy to write recipes, including endpointing. But we've found that the selectivity and planarity can vary depending on the design of the chip, and so it's application dependent. What this means in practice is that even for a single chip, as you go through the very large feature and large spacing metal layers down to the very close spacing metal layers, you may have to adjust the process recipe slightly. And in addition, it's often helpful to just etch an entire chip all the way through and see what the sim signal looks like in order to help you write the endpointing recipe. So as you do this process development, you're going to be consuming some chips. So we at Denton have experience with this, and we have our dedicated tool in the apps lab, so we can help you develop that process either through a demo or at your own site. So another limitation that turns out to not be a big problem is that you can't really monitor the signal of silicon or oxygen. So chips, of course, they're built on silicon. Silicon oxide is the primarily used insulator for the metallization layers, and oxides are throughout the whole chip. And the problem with monitoring silicon is that the mass is the same as N2. And for oxygen, there's always background oxygen. So those signals get confused. However, this ends up not being a problem in practice because every layer has some metal that you can monitor. And metal signals are very clear and far from other background signals.